Okay, so before we discuss the quantum phase transition, let's just summarize the important features of equilibrium phase transitions that we've discussed above. Um, so we said the critical point sits at exactly the point where the competition between entropy and energy is balanced. Okay, so that's where the quantum critical point sits. Um, The other thing that happens is we saw that the two-point correlation function behaves as a power law. So that's what's sitting at the top of the slide over here. But I want to describe what happens close to the critical point and then how you tune to get to the critical point. And typically, when you're close to the critical point, you're not scale invariant. You have all sorts of scales. And one of the things that you could have is a particle mass. So if you have a theory with a massive particle, so a massive particle, and let's say that the mass is m, then what the correlation function looks like, you have s of x, s of y, and it's not a power law, but the way that it behaves, well, so I'm giving you the dominant behavior. There might be some other X dependencies, but the most important X dependence is that it falls off exponentially fast with separation X minus Y. And the thing that determines how fast you fall off is the mass M. So we can talk about a correlation length. So remember what we said the correlation function was doing is S of X points up, then the correlation function tells us how likely it is that S of Y would point down or up or whatever. And if the correlation function is non-zero, it tells us that whatever the value of the spin is at X, it affects the value of the spin at Y. Now, with this exponential fall off, that correlation falls off extremely quickly. So we can talk about the correlation length, and this is the length at which there is some correlation between X and Y. So if I've picked a value for X and I'm within the correlation length away from X, then my spin for Y will depend on whatever X's spin is. But if I've picked a spin X and I'm further away than the correlation length, then Y doesn't care about what the spin at X is. So the correlation length is set by 1 over the mass. And you can see that as soon as the mod of X minus Y is about 1 over the mass, then we've got e to the minus 1. So already this correlation function has fallen off to 1 over 2.7 or whatever it is, and then it just falls off very rapidly after that. So that's the correlation length, and we call that zeta. Now, as I was saying before, you have to tune carefully to get to the critical point. You don't always get there. You have to tune things very carefully. And one of the ways of thinking about what tuning you do, you tune the mass to 0. When you tune the mass to 0, the correlation length diverges. It goes to infinity. And it's when you have this divergent correlation length that the exponential behavior is replaced by a power law. And this diverging correlation length is a smoking gun of the critical point. Okay, so that's very, very important. Now, the divergence of the correlation length is not the only divergence. In fact, there are all sorts of divergences that appear in the usual equilibrium phase transitions. So let's talk about another divergence. Okay, so first of all, let's say we wanted to calculate the expectation value of the energy. Well, what would that be? Well, you'd take a sum over all states. You'd have the energy of the ith state times the probability of being in the ith state. And you know what that probability is. So this is the sum over I. We've got EI. We've got EI. And then that probability is nothing but the Boltzmann factor, e to the minus beta ei. And the partition function, we divide by the partition function, that's the normalization. Okay. So we're not going to do a full course on statistical mechanics now. I'm just reminding you of some formulas that I think you will have seen in your statistical mechanics course. So that's the formula for the partition function. Now, one of the things that is interesting to look at, it's something very physical that we can think about, is the specific heat. So let's think about the specific heat. So the specific heat C, what is this equal to? It is a derivative of the expectation value of the energy with respect to the temperature. So the specific heat is telling you how much energy you need to supply to change the temperature. That's one way of thinking about it. And you can easily remember that beta is equal to 1 over t. So you can easily take a derivative of this expression for the expectation value of the energy. Let's just see, where is there t dependence? Well, there's t dependence in that beta sitting in the exponent. So that's the first source of t dependence. But the second source of t dependence is in the partition function itself. You see, the partition function also depends on beta, which is 1 over t. So I'm going to ask you to calculate those derivatives. It's just simple calculus. And if you do work out what is that derivative, well, the specific heat comes out as the expectation value of E squared minus the expectation of E squared divided by T squared. Now, this quantity, I'm sure you recognize, this is nothing but the variance of the energy. So, variance of the energy. Okay. So, and the actually, when you calculate this quantity, you find out that the specific heat diverges. It gets very, very large. Now, this is what we should expect physically. So why should we expect a very, very large specific heat? Well, the kinds of things that maybe you're used to thinking about. So first of all, okay, let me just write one thing. Let's say if you have a diverging specific heat C, then what does that mean? Think about this equation that I've outlined now in blue. It means, the change in the temperature will be the change in the energy divided by C. So I'm just rewriting that equation a little bit. And if C is diverging, it means that if you add some energy delta E to your system, you hardly change the temperature of your system at all. So you have to provide a huge amount of heat, a huge amount of energy, and you get a very little change in the temperature. And that's what I want to explain now. Why should we physically expect that it's hard to change the temperature of the system? Well, your intuition about changing the temperature of a system comes from things like a gas. So what do you have in a gas? You've got all of these little independent block-like atoms in a gas. What are you doing? You excite these blocks by giving them each a bigger kinetic energy. So that's the picture that you've had so far in your head. Close to the critical point, that's not what's happening. What's happening is you've got these enormous correlation lengths, correlations across all of these scales. We already described that the physics starts to look the same at each scale. And when you add energy to the system, you're exciting fluctuations that are coupled over all length scales. Every bit of heat that you add couples to a hierarchy of domains. So think about our picture of the droplets, okay? You've got droplets on each different scale, and when you're adding that energy in, it's going into all of these different droplets at all of these different scales. And it's for that reason that the temperature does not go up much when you add in the temperature, when you add in some energy, it just gets shared out amongst all of these different degrees of freedom in all of these different scales. Now, another way to write the specific heat, so I'll invite you to check this. It's not a difficult thing to check. It's given as minus T times by the second derivative of the free energy with respect to T. And remember, the free energy is just given by minus 1 over beta times by the log of the partition function. So take two derivatives of the free energy with respect to temperature and make sure that we get the equation that we quoted above for the specific heat. So actually you can see that this divergence in the specific heat is related to a divergence in the second derivative of the free energy. And in fact, when your free energy develops non-analyticities, this is also a signal that you're at the critical point. Okay, good. So there's a few things that I said there that I wanted to say that I didn't remember. So this gave me a chance to say them now. But now let's come to the quantum phase transition. So what is a quantum phase transition? Well, the quantum phase transition it's a phase transition at, so it's a phase transition. Well, let me maybe just write this. It is a phase transition, but it happens at zero temperature, at T is equal to 0. So a quantum phase transition is like an equilibrium phase transition, but just in the ground state. And if you're at T is equal to naught, then obviously your phase transition can't be driven by some competition between entropy and energy. In fact, this phase transition is driven by changing the Hamiltonian itself, driven by changing the Hamiltonian itself. Okay, and I'm going to imagine there's some parameter, some coupling. I just called it lambda. So we would have to tune lambda. Okay, so our usual partition function, what does this look like? It's a trace of e to the minus beta h, or equivalently, a sum over all of the energy eigenvalues of e to the minus beta ei. But because we're at T is equal to 0, T is equal to 0, remember, corresponds to beta is equal to infinity. Well, the only term that's important in the partition function is the ground state. All of the other terms are exponentially suppressed because beta is very, very large. So at T is equal to 0, our thermodynamics collapses to just properties of the ground state. At 0 temperature, the thermodynamics collapses to properties of the ground state. And to detect a quantum phase transition, you would look for a non-analytic behavior in E naught of lambda as a function of lambda, of course, at temperatures equal to 0. Now, previously, we said we could think about the critical point as being very carefully arranged. So if you wanted to hunt for a critical point in the lab, what would you do? You would choose the mass to 0, and when you tuned the mass to 0, your correlation length diverged. This was a sign that you were getting arbitrarily large correlations on arbitrarily large distances in your system. This is ultimately why we were able to get a scale invariant description. So to describe the quantum phase transition, I'm going to tell you what you tune. So as a first step, let's order the eigenvalues, the energy eigenvalues. So the eigenvalues of h of lambda. So the ground state has got an eigenvalue E naught of lambda. This will be less than or equal to the energy of the first excited state, and that itself is less than or equal to the energy of the second excited state, and so on. The quantity that plays a very important role in the quantum phase transition is something called the spectral gap. The spectral gap is usually denoted delta. And how is it defined? It's E1 of lambda minus E0 of lambda. And what I'm going to argue now is that the spectral gap plays the role that the mass m played above, or played above. So let's now try to make this argument. And I want to give you some physical intuition for this argument. So imagine that we've got a gapped quantum system. So we have a gapped quantum system. So what does that mean? When we say we've got a gapped quantum system, it means we've got a quantum system with some gap between the ground state and the first excited state. Let's imagine that the ground state is the state naught. And what I'm going to do is I'm going to disturb the ground state. I'm going to poke the ground state. Disturb naught at x is equal to naught. And I'll do that by applying some operator, O of naught, to the ground state. And then I want to ask a question. So I've disturbed the ground state at x is equal to naught by applying this operator, O of naught. I want to ask, what is the effect in the ground state, but at x is equal to r? And the answer to that question is given by a connected two-point correlation function. So g of r is equal to, I've got the vacuum, I've got O of r, I've got O of naught, and I've got naught. So now I'm learning, if I make a disturbance at x is equal to naught, how does it affect things at x is equal to r? So is there a correlation at x is equal to r? Oh, and I want the connected correlation function. Okay. The bit that really depends on whether there's a correlation between O of naught and O of r. So first of all, well, what does the answer look like? Well, if it's cheap, if it's easy, if it's cheap to excite long wavelength modes, so long wavelength, long lambda modes, okay? And for that to happen, another way of saying this is, i.e., there are excitations of arbitrarily low energy, then the disturbance can propagate very far. Can propagate far, okay? And we get very, in this case, what would we get? We would get a large correlation length. Now, what is the lowest excitation that we can have? Well, it's above the ground state. We need to measure the energy above the ground state. So the lowest excitation that we can have is precisely determined by the spectral gap delta. So if we tune things, if the spectral gap delta goes to 0, then the correlation length diverges. So by tuning this gap to 0, we're going to a point where the system has very, very, very low energy excitations, which means excitations with a very large wavelength. And then the correlation length starts starts to diverge because these long wavelength modes can produce correlations over very large lengths. So that's the story of a quantum phase transition. It happens at temperatures equal to zero. It's not because there's an entropy energy competition at all. Here we start to get the very long range correlations because we've tuned the gap to zero. So we've arranged things so that there are very low um, uh, energy excitations, and those low energy excitations lead to a diverging correlation length. And then once you've got a diverging correlation length, scale invariance starts to appear, and that gets completed to a full conformal symmetry. And once again, the physics of the quantum critical point is described by a conformal field theory, and we again have power laws for various quantities, and we again have critical exponents, and all of these quantities are again computed using a CFT.